Is that
If you
through
share
Zoom?
your screen, should be fine.
Through Zoom? Just
Yeah, great. Welcome, everybody. Dr. Ethan Manilow is a research scientist on the Google Magenta team, where he works on models that can understand musical audio in an effort to make tools that can better assist artists. He has a PhD from Northwestern University and is a co-author of papers contributing to explainable AI, such as AudioLime and MIDI-DSP. Today, he will talk about some of the projects he has worked on, where black box musics, a machine learning system, have been rendered more interpretable, adding more structures to these models.
thank you. And thanks for inviting me to the talk, and thanks everyone for coming. I'm gonna do a quick sound check to see if this works. If not, that's fine. I'll maybe point everyone to a website where they can hear the examples. Great. Yeah, thanks. I'm Ethan. Thank you for coming. I'm at Google DeepMind now. And I'm going to talk about kind of the spectrum of interpretability or explainability for music as it pertains to machine learning. And so why is interpretability important for music machine learning systems? If we look at kind of how musicians perform and what types of things that they find interesting and useful, having a really concrete control over how notes are articulated and how performance happens is super critical for musical applications. So you can look at this in a bunch of different music technologies, ranging back from, violin, which are old technologies, but singers also do this. And when we think about like recording in the studio here, if you can see my mic, there's a bass guitar player. We think about a lot about the sound, right? And so we think about the articulation and position of different microphones. This is made really visually apparent with electronic instruments, where we have a lot of different knobs and sliders and stuff that represent what exact sounds are coming out of the instruments we use to make music. So this type of control is extremely important for many, many musicians, no matter where they are in their musical journey. So we have this type of old paradigm of actually knobs and sliders from the old work in electronics and stuff like that. But when we think about the types of generative models that we're making today for musical systems, the interface looks a lot like this. So we can have long debates about whether this is good or bad, and I will leave that discussion for a different time. But the point I want to make here is that the control you're getting when you're typing in a text box to get some music out is very different from the low-level control that all these instruments that we've created in the past have given us. These systems, however, are as we know, they're big generative models, so they're black box models, but they're extremely powerful. And as these systems are coming out, what seems like on a weekly basis, they're blowing a lot of people's minds, and they're really exciting about what they can do. And I think it's not hard to argue that these systems do have some understanding of the nuance of musical structure and how to articulate notes within them. And so the kind of core question is, how do we get all this good stuff that's in the model out of the model so that we can tweak these knobs and make these things really advanced instruments? And I'm going to submit that the answer to this, and I'm assuming most of you people agree with it, given that you're in this talk, is interpretability or explainability. So a lot of the work that I've done predates a lot of this most recent like generative modeling boom. But I'm going to talk about some of the work that I did prior to that gives us an understanding of interpretability. And then I'm going to submit a potential research agenda that is maybe up to date for the world that we're in right now. So as was mentioned in the intro talk, right, we can think of interpretability or explainability existing on this axis, right, where we have on the one side, we have intrinsic interpretability, where we actually can design some interpretable features into the system such that we know what is actually happening in it. And on the other side, we have post hoc interpretability, where we have no understanding of what the model's actually doing, nor do we care. And we're going to try to analyze what the model's doing afterwards. So on this side with intrinsic interpretability, what we're doing is we're injecting more of our priors, more of an understanding of what the task we want into the system architecture, and therefore we're giving it more structure. And with that, sometimes we get less data requirements, as I'll show with MIDI DDSP. On the other side, by kind of definition, we have more flexibility about what the model can do, and therefore we can build in a lot more expressiveness. But because we're giving it less of a head start, there might be much higher data requirements. And this is what I'm talking about with these more up-to-date systems, these more modern systems that are generating music from text inputs. Okay, so I'm going to broadly talk about three general areas of projects that exist on this spectrum. First, I'll talk about MIDI DDSP. Then I'll kind of clump together two projects that I did that bake hierarchy into these system designs. And then I'll talk about audio line, which is a post hoc interpretability method. First, let's talk about MIDI DDSP. So MIDI DDSP is a generative audio model that turns a set of notes into high quality, realistic sounding synthesized audio. And we have detailed control over many different aspects of this performance, right? So we can get control over what notes are being played, as well as how they're performed and how they're synthesized. So MIDI DDSP is set up in a structured hierarchy. So we have these different modules that are responsible for different parts of the synthesis process. And at each of these different submodules, right, we have an interpretable output. So I'm going to talk about each of these things individually, but we have each of these submodules has both an analysis step and a generative step. So let me make this a little bit more concrete and talk about this audio synthesis module. And as the name kind of implies here, MIDI DDSP is built on differentiable digital signal processing, which came out a few years ago. The kind of core idea here is we want to encode some audio using a neural network, and that neural network has a set of tools in a differentiable signal processor, which is a harmonic synthesizer here in this case, and it tweaks the knobs of the harmonic synthesizer in order to reconstruct the audio. So we consider the decoder of the system to be this synthesizer here. One thing I want to note here is this happens, these parameters happen 250 times a second. And this will be important in a second when I talk about the next module. Coming to that, we have this note expression module, right? So now we're going to take these raw synthesis parameters, we're going to turn them into something that's a little bit more interpretable, or I should say more compact, so that we can have better control over it. So like I said, we started with these DDSP parameters, which are 127 dimensional, and they happen 250 times per second. And what we're going to do is we're just going to, because this representation in and of itself is so interpretable, we can collect a set of summary statistics for this, right? So we can grab things like the vibrato of a note, the brightness, the attack. And one thing that's important here is that we get 6 controls, but it happens once per note. So we can pool these controls of these parameters over these note boundaries. So now instead of tweaking 127 dimensions 250 times per second, a user can just once per note set these values and get some control over the system. And then we do the round trip back, where we actually take these, we have a generative model or a set of generative models conditioned on these 6 controls and produce these DDSP parameters. So to just give you a flavor of what these look like, here's what the note expression looks like for vibrato. If I have these 2 notes, and I can set the control for each of these things individually. So if I set this one really low, 36%, and then I can set this next one really high, 82%, you can see there's a lot more wobble in this note. And then again, if I set these both really low, the vibrato is off, so therefore the pitch is flat. So then I'll talk about this last piece. This piece is actually pretty simple. Once we have these the 6-dimensional representation for each of these different expressions that we care about, we just have a simple RNN that just spits out these 6 numbers once per note. So as I mentioned, right, because the system is so intrinsically interpretable, we've imputed a lot of biases into it. And therefore, we can train the system with a really, really small amount of data. So this was trained on URMP, which in total has just shy of 4 hours of data, and some of these instruments only have 15 minutes of data. So I'll play what some of this sounds like. So this is the original. This is actually output from MIDI DDSP. This is the original audio that that the system produces for this example. So we input this score, and you can see the pitch contour in the spectrogram. Sorry, a little bit of a lag. And now we can edit these notes here. So we can change these notes so they go up an octave. We can change the articulation of these notes in the middle here. So this first one, or the second note, will have a lot more vibrato, and then there'll be a staccato. And then we can change the synthesis. The synthesis really, we can change what instrument is being played. For this example, we switched to a glide here. I'm going to skip this before and after. We just heard this. So this is kind of the core of DDSP, right? We're starting with a piece of audio. We're learning these different representations that we have different interpretability for, and there's black boxes that are in throughout each of these different representations here. So abstracting this a little bit, we could say that there's this. I'm going to call this hard interpretable priors, right? We have some black box, right, that is interspliced with these intermediate representations, and these intermediate representations are waypoints along the way between these black box modules. So this DDSP was forced to use these different parameters in order to do what it's designed to do, which is generate audio, right? And we force these systems to be these representations to be understandable. So now I'm going to move a little bit further to, I guess, my right, to talk about relaxing some of this with hierarchical priors. And these I'm going to call these soft interpretable priors. So unlike DDSP, where we give the system a set of tools to use in order to finish its task, we're going to give it a little bit fewer constraints. I think of this as having interpretability like baked in, but as a suggestion. And so there's no real expectation that we as humans will understand this representation. And I'm not going to go into each of these things, but here's a handful of papers from the literature over the past few years that I feel like exemplify this. So I'm going to talk about two projects really quickly here that incorporate this idea of hierarchical priors. And first, I'll talk about hierarchical source separation. And so hierarchical source separation is built on this notion of source hierarchies, the idea that you can mix together a set of sources that are related, like an acoustic guitar and electric guitar, to get a parent source. And then our goal is to do the opposite, is to separate. Once we have a more broad class, we want to separate that into more specific classes. So we can, given this small tree, right, we can populate this much larger tree of a fuller hierarchy with really specific sources at the bottom, like individual guitars or pianos or electric pianos and stuff like that. And as we get higher and higher, right, our notion of what a source is gets more and more broad until we get to the top, where we have only one source, which is a source and name only, called mixture. And in order to actually uniquely separate along this thing, we need to define a path here, which is uniquely defined by this child node. So we can think of separating hierarchically in two different ways. We can think of this top way, where we have this kind of single level paradigm, where we have individual networks that are responsible at different nodes of this tree. So we have one network per level here, and these are each trained separately. And the more interpretable way is, in the soft priors notion of interpretability, is where we have one network that's trained jointly for all levels. So we enforce that this hierarchical path is understood by this one network. And so maybe shouldn't come as a surprise given where we are, right, that these hierarchical methods do separate better. So at this grandparent level, this highest level of the hierarchy, the most broad level, we get similar results. But as we get to more and more specific nodes of the hierarchy, the multi-level system that has this notion of hierarchy built in retains a lot more performance than the single level system. Okay, so that's hierarchical source separation. Now we'll talk about hierarchical few-shot classification. The idea here is few-shot in this, again, kind of classical sense, quote unquote classical sense, not like in this LLM style where it's trained on everything and you just say, hey, have you seen this before? What we do is we give an example, a few examples of what we want the system to do, and we ask it to, given a new query example, to classify this thing. So here with, this is a paradigm called prototypical nets. We have an unlabeled query, which is this white dot in the center here. And we're going to give it a handful of examples that are called the support examples. And what we do is we make a prototype of these support examples, which is the mean vector of all these things. Once we do this for a handful of different support examples, we get some embedding space here. And now our prediction for this white dot is whatever is closest, whatever its prototype it's closest to. So we can design hierarchy into this as well, right? So we design this embedding space such that it's hierarchical. And what we do is, if you see the bottom here, we make that correlate to, these prototypes correlate to individual nodes in some musical instrument hierarchy. Then we aggregate these nodes along this hierarchy. So if we have 3 different types of reed instruments, we aggregate these prototypes into making a meta prototype, and we can iteratively aggregate these things such that it matches an instrument hierarchy. So this is similar to agglomerative clustering. And then we can also have some design into the loss, right? At any different level of this, we have one task, and right, we can do this cross entropy loss, but we can aggregate these things so that we have this hierarchical cross entropy loss. So we have different weights at different levels of our hierarchy. And when we do this, the performance on unseen instruments is greatly improved for the vast majority of cases that we look at. Okay, so these are these soft hierarchical priors. And the way I think of these soft interpretable priors is that we still have this interpretable structure, right? It's not an explicit tool in like DDSP where it must use this in order to solve the problem. Instead, it's a scaffold, right? So there's still a black box in here, and the black box is going to solve the problem however it sees fit. But we're having a little bit of we're putting our fingers on the scale a little bit just to make sure that it's using these interpretable priors in a way that helps solve the problem. So now I'm going to talk about audio Lyme. So audio Lyme is on this complete opposite end of the spectrum, where we have no understanding of how the model was put together, what types of systems happen in there, and we want to understand the predictions that this model makes after the fact. So Lyme is a paradigm from a few years ago. This stands for Local Interpretable Model Agnostic Explanations. So let me just explain what this is before we even think about audio for a second. So the local means that we're looking at one example at a time here. So let's say we have this example of this porcelain frog that has a heart holding a heart. What we want to do is we want to define a set of interpretable features. I'll talk about that in a second. That's actually a really key part of this technique. We define a set of interpretable features. Here we're going to maybe do clustering in this pixel space. And we represent each of these clusters as a binary vector, whether or not this pixel cluster is present or not. So in this image right here, we have a string of ones, right, because all the pixel clusters are available. So then we have our black box thing, and we selectively turn on and off these pixel clusters. We turn on and off these interpretable feature representations and feed it into the network and get some prediction from the network. We take these collections of these binary representations of what features are available and the outputs from our black box model, and we train an interpretable surrogate model on this, right? So we have some feature vectors here that the interpretable model is going to give us, and we want to choose an interpretable model here, like linear regression or a decision tree, such that when we look at this example, right, we can get some high probability of an explanation given these features that are on, right? And so we can say what features are most likely to give us a positive or negative answer, whatever we care about. And in this case, it's this frog's face. So like I said, it's really important actually to make sure that these features you're defining are useful. And this is non-trivial for audio. So when you think about what happens in the pixel space, a lot of these systems are designed with images in mind first, right? Using those kind of naive approaches to thinking about spectrograms as images, right, does not always work. because of what we know about audio. Audio does not occlude, right? We can hear multiple things at once. Specific sounds and spectrograms are not contiguous. Harmonic sounds, right, have different harmonics that are sometimes completely non-contiguous. So some of the first attempts at doing this in the audio space would use spectrogram patches as interpretable features. So here we chop up the spectrogram into rectangles, and this ignores kind of the inherent features of audio that I was talking about. Furthermore, it does not prioritize the listenability when I'm going to term the listenability of examples, right? Instead, you say, hey, here are these audio patches, or here are these spectrogram patches that are your model cares about. But now these are band limited, right? And maybe give you some understanding of what's going on, but it's not audio in the sense that people are normally listening to things. So as you can see what I'm setting up here, audio lime, the core idea is to use separated sources as features, right? So now instead of using spectrogram patches or treating the spectrogram as an image, right, we're going to do something native, similar to you can think of like image segmentation would be an analogy of source separation. We're going to use these sources as our interpretable features. And so kind of by design, right, this accounts for this non-occlusion of audio and this non-contiguous spectrogram reasons. Additionally, we can now listen to each of these things. So we ran a little bit of experiment, and this takes a little bit of explanation here. What we did is we took a music tagger. We have some black box model, and we put some outputs, input about 100 outputs from the music tagger into Slime or Audio Lime. And then we only, given one of these explanation things, methods, we're only going to take the top K most prominent features, and we're going to put it back into the music tagger, and we're going to calculate how many times the music tagger matches. So how well, given only the top K set of explanations, how often does the music tagger make the same prediction as if it were just predicting in a normal setting? And as you can see, Audio Lime here, which is this blue, we tried for 2 different audio taggers. Audio Lime, given a number of K interpretable components that we changed between 3 and 11, Audio Lime consistently ranks above this Slime method. So in post hoc interpretability, right, we make no assumptions about this system, right? This music tagger that we looked at could have been anything. And what we're going to do is really going to inspect the inputs and outputs. There's a notion of locality here, than which we're looking at only one example at a time. But I think there are other methods that are a little bit more global. So here we are on the spectrum of interpretability. These are the 3 types of flavors that I've talked to you about today: MIDI, DDSP, hierarchical priors, and Audio Lime. I want to spend a few minutes bringing us back to where we are right now in the world. Where we are right now in the world with this world of generative music models that are really capable, and kind of outline where I think there are gaps in the literature and where interesting research could happen. So again, we're talking about this world where we have these text to music systems, these giant black box systems that produce high quality musical audio. And I'm going to posit, I'm going to submit to you that these systems do have some really fine notion of musicality in them. They can make really interesting music, right? So therefore they must be tweaking the synthesizer settings, so to speak. And I think one way that we're not really looking at the system is through the lens of mechanistic interpretability. I've seen some steps into this world, but I think there is a huge opportunity here for mechanistic interpretability with these audio models. And so for those of you who don't know, mechanistic interpretability is this research path that has been pursued, and from my understanding, initially by Chris Olah initially at OpenAI and now at Anthropic. And the goal is to reverse engineer these neural networks. So they discover these things that they deem circuits, which are connections between neurons that these sub-networks within them that encode, as they call, meaningful algorithms. So they can do edge detectors, car detectors, things like that. If you look at these old networks like Inception, there are more more robust or more modern systems that they look at, like GPT-3 and stuff like that for language. And so this is an image from 2020, which is over 4 years ago now. And so there's been a lot more research in this space. So the first goal is to reverse engineer these networks and discover these circuits. And the way I see it, a second goal should be to actually start editing these models, right? Do what I'm calling circuit bending. There's some other research in image space, right, where we can edit a generative image model. So on the left here is an unmodified uh, GAN that generates churches, and they modified these networks here such that said, hey, the tops of these church steeples should always be trees, and now every time it generates a church, right, it has a tree at the top of it, which is something that never happens in the real world. I think there's a real opportunity here for music and art and thinking of these things as musical instruments to do really fun, crazy things with these extremely powerful models. And this is something I'd love to see in the world. Please, if this interests you, come chat with me afterwards. I don't have anything. I haven't really started thinking about this other than this talk right now. Anyway, that's it. Thank you so much.
Yeah, so I think we have time for a few questions. Like, are there any questions from the audience?
Thank you, Ethan. My question is, are there any features you think could be useful for controllability other than, let's say, for now, people are using text, people are using chroma. Do you think there's anything that can give us more controllability right now, like Indidius use volume, vibrato, stuff like that? But there's still a lot of limitation on what we can actually tell the network we want.
Yeah, I mean, I think the limiting factor here is data, right? We use chroma because that's easy to extract from audio. But if you had a perfect, music transcription system and you could transcribe every piece of music in the world, right? You could use that as a feature. If you had a perfect system that could tell you the vibrato for every single note, et cetera, et cetera. The trick here is finding clever ways to extract that from data, or making methods that actually or data sets that actually have those things built in. I don't think there's one perfect feature, just like there's not one perfect instrument for every musician. There's going to be things that fill different niches that I think it's important to think about for a broad stretch of music and musicians.
Are there any more questions?
Following up on that, we how do I put this? I feel like there's a lot of emphasis in the world, at least the people I hear talking about it, are always trying to make these things interpretable and controllable by essentially novices. And then there's a smaller group of people that care about, like, expert, for example, music practitioners, like, say, professional musicians. I'm wondering if you have any thoughts about either interpretability or controllability on this sort of spectrum. What are the tensions there between making something interpretable or explainable for a novice versus an expert?
Yeah, I think this is a really important kind of spectrum to think across of when we think of making these systems, because I think of these things as musical instruments, plain and simple, and you can think of the musical instruments that exist out in the world, like that are maybe easy for novices to pick up. One I can think of off the top of my head is the ukulele, and then really difficult instruments like maybe violin. I don't know. Debate me on whether those are easy or hard, but the point is each of these things, I think it's not obvious a priori which types of people are going to be attracted to what types of interfaces. And so I don't really have a good answer for that, right? It might be that, like, these text and music systems, maybe there's a set of really expert musicians that latch onto these because they like the dice roll of these systems, but it might also be, and obviously they're really well suited for novices because you just type what you want to hear. But it might also be that like if you have a system with a billion knobs and stuff like that, that might create an on-ramp for people that are novices to learn and explore more about music. So I think it comes down to a case-by-case basis. I don't think there's any like kind of broad rule that I could outline here that I would be able to argue is the right rule for every person.
So thanks a lot, Ethan. So we are really packed schedule, so we will move on to the next speaker, and feel free to reach out to Ethan.
Thank you.
All right, so we will move on to the next.